Okay, today we're going to talk about transient systems. Now, this is going to be a new material. It's going to not be on the test. It's going to be given to you on Monday. But transient systems are really very prominent out there. After you deal with there's going to be a transient part about every system until it gets to steady state. Transient to ramp it up, steady state, transient as you go down. But there are some systems that are very obviously just transient the whole time they're dealing with, and so we're gonna look at those today. And so let's talk about how we're gonna do a transient analysis. We're gonna look at the continuity equation and the first law of thermodynamics. So let's look at the continuity equation here first of all, and I'm gonna put spaces in this equation on purpose here. So I say, whoops, let me change my pen color. The change in mass of the control volume with respect to time equals the summation of the mass flow rate in minus the summation of the mass flow rate exiting. This is our first law. Now, transient means that we're changing this over time. So what we're going to do is we want to integrate this. We're going to integrate this from 0 to t dt, from 0 to t dt, and from 0 to t dt. We want to add up and see how it's changing over time. Okay, and when we do that, that's an integral. Now look what happens when we do that. First thing that happens is this dt goes away. This dt goes away. And so when we look here, this is going to be equal to the integral from 0 to t, the change in mass of the control volume. Okay. Now let's look at the next thing. Let's look at the summation of the mass flow rate in. Okay. This is mass per time, right? And as we're integrating that, we can figure out what that is going to really tell us. If we see mass per time, we can really understand what this is going to give to us. Okay, so let's do the first integration, which is really easy. The change in mass of the control volume. This is going to be the mass of the control volume at time t minus the mass of the control volume at time 0. Okay, not times t, at times t, as a function of t, minus the mass of the control volume at time 0. Okay. Now the next thing is going to be the summation. This is going to be equal, basically, we'll consider the mass flow rate to be constant, so we can take it out of the integral. We can say this is going to be the mass flow rate in times t minus 0. Okay, we take the mass flow rate out of the integral, and that's what we have. Minus the summation of the mass flow rate exiting times t minus 0. Okay, now what I like to write this is in a little different way. I like to write this as the mass of the control volume at time 2 minus the mass of the control volume at time 1. Okay, because that's really what happens. Mass control, we have look at state 1 and state 2 as time 0 and time t. That's what we're going to be looking at. So I'm going to rewrite them as 1 and 2. And this, if I take the rate of the mass flow rate times the time that it's applied, I don't get a rate anymore, I get a mass. So what I'm going to get is the summation of the mass in minus the summation of the mass exiting. Okay, and we've looked at this and understood this for many, many times. This is our transient equation. Okay, and it makes sense to us. The mass of the control volume at state 2 minus the mass of the control volume at state 1 is going to equal what mass comes in minus what mass goes out. You could probably derive this equation just by thinking about it as we get going and understand this. Okay, that's a really straightforward equation. Okay, let's look at the energy equation. The change in energy of the control volume with respect to time is equal to Q dot, the control volume, minus W dot of the control volume, plus the summation of the mass flow rates in, enthalpy in, plus the kinetic energy in, plus the potential energy in, minus the summation of the mass flow rate exiting times the enthalpy exiting, plus the kinetic energy exiting, plus the potential energy exiting. Okay? Now, remember what we said here, that this energy of the control volume, this is going to really be equal to internal energy plus the kinetic energy shouldn't say V2, plus the potential energy. That's really what that is. We're putting it into shorthand up here, we say the energy of a control volume. Okay. Now, I'm going to make a assumption here. Assume that kinetic energy and potential energy effects are going to be negligible. Okay, we're not going to be dealing with kinetic or potential energy effects. And so when we do that with our equation, we get rid of this and this and this and this. And we also get rid of these two items here. And that leaves us with now our first law equation. It looks more like this. The change in internal energy of my control volume with respect to time is equal to Q dot minus W dot plus the summation of my mass flow rates in times my enthalpy in minus the summation of my mass flow rate exiting times my enthalpy exiting. That's going to be my equation. Space is put in there on purpose. Because again, I want to add up and see how this is changing with time, so I'm going to go from 0 to t dt, 0 to t dt, 0 to t dt, 0 to t dt, and finally 0 to t dt. Again, we'll be able to cancel off our dt's, and our first integral is going to be very straightforward to figure out. It's going to be the internal energy of the control volume at time t minus the internal energy of the control volume at time 0. Okay? Our next equation. Remember when we took this before, again, we're going to assume that the heat transfer rate is constant. We're going to move it outside of the integral. So a constant heat transfer rate, and then we're going to have from 0 to t, and that, if you take the rate times the time it's applied, all you're going to get here is Q, not Q dot, heat transfer. If you look at work and see how much the work is, the power and how long that power is applied, you just get work. And then here, same thing, we're going to have that the mass of the flow, mass is going to come out here, and we're going to get summation of the mass in times the enthalpy in minus the summation of the mass exiting times the enthalpy exiting. That's what that integral is going to give you. Now in here we've made a very important assumption that I'm going to have to indicate to you, and here we're going to say we're assuming that H in and H exiting are constant. That's the only way we can take them out of the integral and do this. We're going to say while whatever's exiting the control volume has a constant enthalpy, whatever's entering the control volume has a constant enthalpy. Now we can do problems where they have a variable enthalpy, but boy, they are fun. They are a challenge to do. Okay, so we don't want to do those if we don't have to do those. Okay, and so here's our equation. Is going to come down to this. It's going to come down to internal energy of our control volume at state 2 minus the internal energy of my control volume at state 1 is equal to Q minus W plus the summation of my mass flow rate, mass in, enthalpy in, minus the summation of my mass exiting, enthalpy exiting. This is our equation. Okay, so now really we have 4 states to worry about. State 1 and state 2, the inlet and the exit state. Okay, whatever's coming in or whatever is exiting. And this is how these 2 equations will always simplify. Now you can memorize this, of course. I think that some of you will. But I would ask for you to actually go through it a couple times just to get comfortable with that process and see how that goes. Okay. So the first thing we're always going to do in a problem is get to these 2 equations. These 2 equations are always how we're going to get to the 2. And we have to remember our special case that we're talking about here. Kinetic and potential energy effects go to 0. We're assuming that the rates of everything are constant. The heat transfer rate, the rate of work, which is the power, the mass flow rate in or the mass flow rate out is a constant. We're assuming that the enthalpy or the properties going out are constant and the properties coming in are constant. That's what we're assuming. Okay, when we do this. So this is a special case equation that we need to worry about. Okay? Now, what do we do now after we get these 2 equations? The next thing we do after we derive these equations is now we simplify. Okay? We simplify. So let's assume for our problem. So let's assume that this is our situation. In fact, let's just do a problem. Let's just do a problem that does this. Let's take a problem that has a well, here's what I'll do. I'm going to pause right here, stop right here, and then I'm going to do a problem so that we can do it on our next video.